talked so far about the introduction division. Now we're going to go on and look at the second division. Method for science, process for most of you for engineering. And in the book I talk about the fact that in this division you're trying to make the claim that your work is connected with what has gone before. It has to be connected. If it's just totally unknown, you still have to make some connection. All of our knowledge is connected with other knowledge. So you have to somehow connect it with what is already known. But it also has to be distinct. It has to be new, or there's no reason to publish. So, again, from the textbook I say, the second division does not merely report what you did. More importantly, how it is connected to yet distinct from previous research. Okay, so again, a lot of people, when they look at method and they think, method, I did this, I did this, I did this. So what? Why do we care? So you have to show not just what you did, but why you did it, how it's connected, how it differs, how it adds to knowledge. Okay, so you have past research, you have your present research, and you have this foundation. And so one way of describing this was developed by a former TA, said, if you look at all of human knowledge, some of it everybody knows, just common knowledge, at least everybody in one society. And then as an undergraduate, you learn a little more, and you learn sort of, specifically about engineering, science. You learn a little bit more in some direction. And then as a graduate student, in graduate classes, you learn more in that particular direction. And then as you read research papers, you read right up to the very edge of what is already known. You're reading the newest, the latest, the best thing, and if we expand this part and look at it, you're going to divide that into, this was already known, but it's not good enough. This was already known, and I'm going to take it one step farther. I'm going to push the boundaries of what is known just a little bit. That's what your research is doing. So you're building on the deficiency, you're building on the foundation, you're pushing something new just a little bit. Okay, so like with Wenhui's paper, I told her that she's got 2 topics in one paper, and it's too much. You can't put too much in one paper because it becomes too long. It becomes a thesis. All right? But so I suggested you have to break it into 2 papers. Each paper just pushes a little bit. That's, again, very hard for graduate students to learn. It's really just a little bit. That's all you're doing in any one paper. Okay, so what you need to show in the method section is reliability, or in the process, feasibility. If you remember, going back to the idea of claims, implicit claims. In the second division, you're trying to show that you have gathered data in a valid and reliable way. So the way you do that is you use a valid and already accepted method. You do it very, very carefully, therefore it's valid and reliable. So your method section says, we're using this method, we did it very carefully. You don't say it quite like that. You say, we measured, we recorded. You use all those terms to show that it's reliable. In engineering, you have to prove that it's possible. You develop a workable solution. In testing, you're going to look and say, it's better than the current. But first you have to say, it works. Okay? So again, that's your goal in this division. So again, going back to science. Science, the methods division usually has research details and testing methods. Both of those are things that have been done before. And so you're saying, I followed the past methods, I just changed a few parameters. I changed the organism, I changed the length of time, I changed the environment, I changed some small thing, but I'm using this basically valid, accepted method. So you emphasize how similar your work is to past work, and you emphasize, in my present work, I paid very close attention, measured carefully, did all the things properly, so you can accept it. The data are good. All right. Engineering is different. Engineering, you're building on past research with modification. And it's the modification that's important. So you're emphasizing the difference, not the similarity. And you're emphasizing your achievement of the research goal rather than the care with which you did it. It's a different emphasis. And so again, the components that we find in the second division, for engineering, we often have foundation. And foundation, again, may have 4 different parts. The accepted procedure talks about following proven methods. That's basically, again, what science does. In engineering, you're more likely to have problem formulation, where you take this approach and you extend it. We are going to take this and we're going to define a new problem that we're going to solve to extend that knowledge. Or you build on an accepted theory, basic electrical theory of how the Doppler shift or whatever. It's well known, it's well established. We know because of that, things ought to work a certain way. So we build on that accepted theory. And then justification would be, there are several methods that we could use. We could use this method or that method. Within this approach, we can try 3 different things. We're going to choose the best method. So all of you, some of you have different aspects of these different things. But all of you have something about the foundation. Okay? So again, this is from the textbook. You'll notice that there's a lot of overlap between A and B and C. Okay? This is accepted procedures or methods were followed. This is built on an existing approach. This is based on an accepted model. So what's the difference? The difference is more that C is more based on, again, basic theory. Okay, it goes back to, again, the Doppler shift in Charles' case with satellite movement. Well-known, established theory rather than specific things that have been done, like when Hui is building on the GPT models, you're building on specific software, specific algorithms that have been developed before. those specific algorithms are like probably problem formation. The general knowledge is C. Just different aspects of the same thing. And then justification again. There are different ways to do it, which is best for us. All right, so again, framework is sometimes, or foundation is sometimes very hard to find in a paper. So let me try to explain it this way. The deficiency points to problems with the current work. The research detail says, this is what's new about our work. And the foundation bridges that gap by saying it has some advantages over previous approaches. Okay? So it's saying there's one of these previous approaches which is pretty good, so we're going to make it better. And that then is your foundation. So you have lots of different things have been done, but there's something that hasn't. And so that's our goal. But that's built on the same foundation as something that's been done before. It's very rarely totally new. And if it is, John is developing a new method that is new. So he's going to have to say, this has been done, this has been done, this has never been done, no one has done it, to the best of our knowledge, nothing has been done about it. He's going to create a research gap rather than a deficiency. Okay, that's the difference. Science and some new ideas in engineering create a gap. But most of the rest of you are saying it's good, but not good enough. A deficiency. All right? Again, just different ways of approaching the same thing. All right, so again, how do you distinguish foundation? If you look and it talks about citation of something and it says, this had problems. That's talking about deficiency. If it said, this is good, and it doesn't really talk about deficiency, that's probably the foundation. And it's often the one that's mentioned just before the research goal. The other way is to look at it, is it the current research, that's your research details obviously, or is it something that other people have done and we are following in their steps, we are then going to go beyond where they stopped. That's the foundation. Okay, so we may not say, you know, I'm going along, they stopped here. Sometimes you don't say they stopped here. You just keep going. Some papers don't mark that division very well. That's one of the questions that I ask you to look at, is how well do they mark that division between past and present? Okay, we'll look at that one next week. Okay, so the research details, there are lots and lots and lots of ways of doing research, right? So this is really hard to, you know, to make subcomponents, because there's so many possibilities. This is my best guess so far. In science, you often have materials and methods. So you have the names and sources. We got this from here. So we know that the material is good. We followed this basic method. This is the two parts that follow basic most science. Science may also have things like site or participants. If you have environmental work, it's dependent on where it is, the site. If it involves people, you have to say who the people were. Again, these are less common, but if they're important in your work, you have to put them in. And then engineering, most of the rest of these relate to engineering, because that's the focus of the textbook. So you have the new design, you have new math, a proof or algorithm, maybe a new problem, okay, computer science, often with computer security. No one ever thought about this until somebody hacked into this system, and then we realized, here's a problem. And just before you can solve the problem, you have to identify the problem. And that identification can be enough for one paper. And then this last one is intermediate testing, where you set parameters. So you have your design has 5 parts. You build the first part. You test, do I want level A, B, or C? B. You build the second part. What level do I want? A. You build the third part. You're setting the parameters for each of those parts separately. And then you put the whole thing together. So it's not your final testing. This is usually found in the process division. So with your work with AI, as you are training, you're going to train and see the results. Train and see the results until you say, good enough, let's try it. So those are your intermediate testing. So the reason I have these in a different color is these were added. They're not in the textbook. Okay? These are the ones that are in that new sheet that I want you to use. So that's why it's important. So again, what does intermediate testing mean? Before your final design, before you test your final design, you got to test all those parts separately. That's the intermediate testing. If there are results that are reported, well, I mean, I could create a new category, but I don't want to. So we're just going to call them data. All right, so you will potentially have, because often it doesn't show the final data in the intermediate testing. Sometimes it does, but often it just says, this was best, we chose this. It doesn't show the actual data. If it does, call it 7. Okay? Again, note as you're looking, most tables show data. But sometimes tables show parameters. Parameters are not data. Data are what you get out, the results. Parameters are what you put in, your choice of conditions. So even though they both look like tables, they're very, very different. Keep that in mind. Okay? As we're looking at this section, if I see tables of parameters in your work, I'll point it out to you, because it's important to recognize what those are. So again, the parameters will be counted as inputs, either usually your method, your research details, or the way that you're testing it. Whereas the data are the data patterns. So testing methods, again, different testing methods. With physical testing, you have a real device. You have verifiable procedures. Physical testing is used in both science and engineering. Data set testing and simulation testing are common in engineering. What's the difference? They both are done on a computer. I first called this computer testing, but that was confusing because these are both done on a computer.
Yeah.
Simulation means you set up a model, essentially, on the computer, and you run the model. Data set testing uses a standard data set. I think Joe's the only one that's using a standard data set in here, the only one doing data set testing. If there's data set testing, it will say, we use this standard data set. Almost like 99% of the time, it should say that. So if it doesn't say data set, it's not data set testing, it's simulation. What is a data set? Well, when you're comparing different programs, you have to test them against the same data. The only way you can do that is if you have a standard data set. So this is used extensively in computer testing. Computer sciences uses this all the time. Most other engineering doesn't. And then statistical tests are pretty much restricted to science. Statistical tests are things like, if you see anything about t-test, chi-square, analysis of variance, regression, all of these are statistical terms that you probably won't see in engineering. Only about 5% of engineering papers have statistical testing, in my experience. But if you see any of those and it talks about a test that seems to be mathematical, ask me, and again I can check and see if that is. There are names of a lot of these listed in the textbook. Okay, so again, data set testing involves a standard data set, I just said that. So again, I changed these names because they cause confusion. And I mean, that's what good teachers should be doing, is always updating, trying to improve. Okay, so this division is where we see the greatest difference between science and engineering. In terms of similarity to other papers, the method section in a science paper they're almost identical. I mean, this is where science papers, if you run it through Turnitin, will often have 10 to 15% similarity. And most of it is in the methods. Because there's only one way to say boil something and decant the liquid. You know, I mean, there's only one way you can say it. So the similarity to other papers is quite high. Whereas with process, it's your design. It's brand new. It's going to be different in most cases. What about the length? Well, again, methods, it's an established method. The whole method was put in some other paper. So we just cite it and we say, go look at this method. We don't have to put it in ours. But in the process division, that development of a new thing, that's what's important. All right, so it's very long. The importance of the division, again, the method section, sometimes it's hidden at the back of the paper. It's put in small print at the very end, because nobody reads it anyway. Whereas the process, I mean, that's what you read. You read what are the details of this. And then the style, particularly in terms of introductory paragraphs. With the method, it just, we did this, 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 we did this. No introduction, no summary, just basically a list of we did. But with the process division, you're leading them through new territory. So, you know, this is like, I use the illustration of GPS. If you're going from here to the dorm, you don't use your GPS. You turn it off. Because, I mean, everybody knows, you know, you don't need, you just say, oh yeah, I go past the administration building and past the, everybody knows where those things are. If you're going to some small town out in the, you know, in the mountains, then you turn on your GPS or your, you know, your Navi system of whatever sort, and you say, and the navigation system says, in 100 meters, turn left. So you know when 100 meters from now, you're going to have to turn. You warn people where you're going, so they're ready when they get there. That's what this introductory paragraph does. Some of your writing, again, in the process division in particular, you have section 2, 2.1, 2.2, 2.3. But before 2.1, you have a paragraph that says, in this section, we will do 2.1, 2.2, 2.3. Why? So people know what's coming. Same thing. All right. I'm going to do a short evaluate your understanding today. This is basically what I just talked about, but why are organizational features like summaries and topic sentences more important in the second division in engineering? Okay? Take a couple of minutes and make sure that you and your partner understand that. Talk.